Right, so a quick question, are you able to see my screen? Can you hear me properly? And
yes,
you as well?
Yes, everything is okay. Please go ahead, start.
Perfect, thank you very much. So hi everyone, my name is Jay Kalinani and I'm a second year PhD student at the University of Padua, Italy. And firstly, I would like to thank the organizers for giving me this wonderful opportunity. And today I'll be talking about the role of magnetic fields in binary neutron star merger simulations, focusing majorly on the results presented in these three papers based on the work done by my PhD supervisor, Dr. Riccardo Ciolfi, and our collaborators, Professor Bruno Giacomazzo and Dr. Wolfgang Castan. And I'm also leaving these archive references here in case you want to check these papers out at a later point. So magnetic fields are indeed fundamental physical ingredients in binary neutron star mergers. In such events, strong magnetic field amplification is indeed expected to occur, leading to magnetic energies of the order of 10 to the power 50, 10 to the power 51 ergs after merger. Now, such a high magnetization can have a direct impact on the dynamics of the remnant system, as well as the related processes like matter ejection in the post-merger phase. Moreover, strong magnetic fields can be crucial to explain the formation of relativistic jet. Now, the ground-beating detection of gravitational waves from the merger of two neutron stars, also known as the GW170817 event, was also coincident with the short gamma reverse GRB 170817A, accompanied by an optical infrared transient AD 2017 GFO, giving us the long-awaited smoking gun evidence connecting binary neutron star mergers to short gamma reverse, as well as radioactively-powered kilonovae. This indeed opens new doors to multi-messenger astrophysics with gravitational wave sources. But this event also left behind some fundamental questions, open questions, regarding the mechanisms that produce the short gamma ray burst, as well as the kilonova. So to address these questions, numerical relativity simulations of the merger process become crucial. And regarding that, the magnetic fields can act as a key ingredient that cannot be ignored. So in this short presentation, I would try to cover some of the basic ideas and aspects that come out of our latest merger simulations. And one thing that distinguishes our simulations is a very long post-merger evolution that gave us, that allowed us to get some novel insights on how this magnetic field evolves in time and how it impacts the system at later times. So here on top, you see the rest mass density evolution on different timestamps on meridional and equatorial plane, which goes up to about 100 milliseconds after merger. And in all the simulations that I'm going to discuss, the merger produces a differentially rotating metastable supramassive neutron star that is expected to survive much longer than the simulation timescale before collapsing to a black hole. Below, you see the meridional mass distribution on much larger scales, roughly more than 3,000 kilometers, for another simulation, which went up to more than 250 milliseconds after merger. One also interesting aspect you see is that how this matter ejection is quite isotropic, at least close to the remnant system. So to briefly describe the numerical setup that we assume, we perform these GRMHT simulations using the numerical relativity codes, Einstein toolkit, and Whiskey MHT for binaries having mass ratios of 1 and 0.9, and having a chirp mass that is consistent with that of GW170817. We use the piecewise polytropic approximation of the APR4 equation of state for the neutron star matter. And we generate the initial data using the publicly available code Loren. Finally, we add magnetic fields to the initial configurations of our neutron stars as internal colloidal fields, as you can see in this picture here, having the maximum field strengths of 1, 5, and 10 times 10 to the power 15 Gauss. Now, you may wonder, this is indeed why such a high magnetic field strength, as these values are quite much higher than what is expected before merger. Now, the current resolution in our simulations is insufficient to fully capture the main magnetic field amplification mechanisms that happen over small scales, as I think this was also talked about in the previous talk. So here we have the resolutions in our simulation, which is of the order of 200 milliseconds to 200 meters. So this is insufficient to capture these small scale amplification, and hence in order we have to as we want to study these highly magnetized post-merger systems, we make this choice of having a high magnetic field from the beginning. Well, indeed, this is a problem that is affecting all merger simulations performed in GRMHD, and even the highest resolution incorporated remains insufficient. And I think also this was previously talked about and also was discussed on the first day during the breakout sessions, that also there are different groups that are working on alternative approaches of implementing subgrid models to capture these small scale amplification. But here for our simulations, we just adopt a higher initial field. Now, the magnetic field amplifications that I was referring to here are the Kelvin-Helmholtz instability and the magneto-rotational instability. There were some beautiful movies shown by Francois for how the magnetic Kelvin-Helmholtz instability develops. So this is when at the merger, when this KHI develops, when the two neutron star cores come into contact. So in the shear layer of that. And later on, MRI takes over as the dominant amplification mechanism. Now, due to the in the early phase, due to the lack of resolution, we are not able to fully account for all the amplification. But at later on, we reach a stage where the further MHD evolution is very well captured. So on the right, you see the wavelength of the fastest growing MRI mode over the grid spacing. And about 30 milliseconds after merger, MRI seems to be very well resolved everywhere, except in the central region core region of the neutron star remnant. And this is where we have the angular velocity growing with the cylindrical radius. So MRI doesn't get activated anyway. So in particular, here you see in the purple region, the wavelength is covered by at least 10 grid points to about 1,000 grid points. So this gives us the confidence that the further MHD evolution and the features that are emerging are reliable, at least qualitatively. In this slide, I show the time evolution of the magnetic energy for different simulations. So the first interesting thing that we notice that comes out of running very long simulations is that there is a flattening in the magnetic energy. So which starts happening about 50 milliseconds after merger, hinting towards a physical saturation. Now, this shows that the magnetic field no longer remains a small perturbation, but can have a direct impact or feedback on the system. Moreover, we notice that there also exists an absolute upper limit for maximum magnetization that can be achieved in binary neutron star mergers, which we find is around the order of 10 to the power 50, 10 to the power 51 ergs. The second point is on the outflow of mass. So here on the left, you see the radial distribution of unbound matter. And here on the x-axis is the radial distance, and on the y-axis is the time. And this is for two cases. One is the magnetized case with the initial magnetic field of the order of 5e15 Gauss. And the bottom one here is for the non-magnetized case. So in addition to the dynamical ejecta, which comes out first and is not much affected by the magnetic fields, we see that they're here for the magnetized case. There are strong, continuous magnetically driven post-merger winds absent for the non-magnetized case, which contribute to the ejection of mass. On the right, we show the time evolution of cumulative mass flow at different radial distances for these two cases, the magnetized and non-magnetized. And this is a total mass outflow and not just the unbound mass. So this is bound plus unbound. And here you see, for example, about 295 kilometers of radial distance for the magnetized case, and about 150 milliseconds after merger, the outflow is about 0.2 solar masses, while for the non-magnetized case, it remains lower than 0.1 solar masses. Below, you see the evolution of the density along the spin axis, or the z-axis, for the magnetized and the non-magnetized case as well, at around 40 kilometers and around 300 kilometers from the center. So here, indeed, we find a first indication that for the magnetized case, the outflow is quite higher along the spin axis, and this has a consequence that it can pollute the environment along the funnel, along the spin axis. And this has a critical consequence, because this baryon pollution can hinder jet formation at later times. Sorry. So going deeper, we study the remnant structure and matter distribution around the remnant on smaller scales. So about 20 milliseconds after merger, we see that the remnant has a nearly spherical core attached to a torus-shaped outer envelope. So this is for the non-magnetized case as well as for the magnetized case. But at later times, when the magnetic field becomes dynamically important, we see that there is a more isotropic distribution for the magnetized case, while for the non-magnetized case, this remains, the geometry is kind of preserved. So strong magnetic fields can lead to a rather isotropic and dense cloud of material surrounding the neutron star remnant. One particular thing I would want to point out is that here we do not account for other effects like neutrino radiation that was much talked about in the previous talk as well. So which has the tendency to maintain a low can have a tendency to maintain a low density funnel. But we do not know how this effect could significantly alter our current results. And this is a matter of future investigation. Finally, and lastly, let's talk about the magnetic field structure and the geometry. So on the top here, you see the evolution of magnetic field lines for our 2019 simulation. And this is close to the remnant. So indeed, there is a strong toroidal field developing, strong amplification around the equatorial plane, developing a toroidal field, and a growing transient helical structures along the spin axis, developing a poloidal field, which get slightly disrupted towards the end of the simulation. But on larger scales, these field lines extend to more than 100 kilometers, hinting that there is indeed an emerging global magnetic field having an average poloidal strength roughly of about 10 to the power 15 Gauss by the end of the simulation. So for our most recent simulation, which was we see here at much larger distances and large scales and at much later times, a global helical magnetic field line structure can fully develop thanks to the continuous winding action of the differential rotation of the neutron star remnant. And this is a very interesting indication in the context of the short gamma ray burst burst jet production, as well as how this can further enhance mass ejection at later times. So tomorrow, Dr. Tolfi would talk much more in detail about these results in the context of short gamma ray burst, as well as kilonovae. Today, I would just like to point out a couple of things. So the first thing is that for our low magnetized, for our analogous simulation with lower initial magnetization, we did not see any signs of such a helical structure. So this result is not always guaranteed. And sorry, this depends on the very complex interplay between the growing poloidal fields and how the counteracting or the opposing effect of the cloud of material that is surrounding the neutron star. Secondly, as you see here, the isodensity surfaces in gray and in red show how the matter is remains isotropically distributed. And so this effect of these helical structures is not related or associated to any disk-like structure. Lastly, and most importantly, any ordered structure along the spin axis takes time to build up. So this, in our simulation, we find is the order of 100 milliseconds. So to summarize again, and I would like to emphasize again that magnetic fields do play an important role in binary neutron star mergers, and their evolution should be taken into account throughout the merger process in order to better understand how they relate to different aspects like short gamma ray burst jet formation and matter ejection in the massive neutron star phase. So we followed this path and performed GRMSD simulations in having much longer post-merger evolution that helped us to gain a better insight on how the impact of magnetic fields on the systems in hand. And finally, because of such a long merger evolution, we also understood that what is the time scale required to see when these helical structures can emerge, and other aspects as well. So what are the most important urgent missing ingredients that are missing from our simulation and that should be incorporated to see how our results change? The first two here, they are listed below, and the first two here are the implementation of the temperature and composition dependent equation of state, as well as the neutrino radiation. So on that front, there was an interesting talk by my colleague, Federico Cipolletta, about a new GRMSD code, Spritz, along with the implementation of a neutrino leakage scheme, which is still being tested. And for our near future, our future goal would be to perform binary neutron star mergers with neutrino radiation as well as magnetic fields. Another interesting thing could be the having these magnetic field lines extending to the exterior of the neutron stars before starting the merger simulation. So this could be the force-free implementation. And lastly, also neutron stars, starting with non-zero neutron star spins could be very interesting. So with that, I stop, and thank you very much.
Thank you very much, Jay. So we have already a couple of questions. So Julian.
Right. A very interesting talk. Could you tell us what was the orientation of the magnetic fields in the neutron stars at the beginning, when it was in the binary?
Right. So this was essentially based on, so we implemented these colloidal fields, which are limited to the insides of the neutron star.
What was the orientation? They have a direction.
So we did not take any spin effect. So if you're talking about that, so if anti-aligned or aligned, is that what you're?
Well, there are a number of special directions here. There, for example, to start with, there is the orbital axis.
Okay.
And then the structure of the field looks like you've made something like a dipole in the interior.
Right.
That has a direction. And of course, the directions in the two neutron stars could be different from one another.
Okay. Okay.
So just what did you choose them? How did you choose them? And have you ever explored turning them in different directions to see whether it matters?
So I think they were aligned like this with the parallel to the orbital plane, as far as I remember. But
the orbital axis, probably.
The orbital, yeah, the orbital axis, yes. Yeah. But this is as far as I remember, but I'm not completely sure about this, so I have to recheck.
So maybe if I can weigh in, I can just confirm, yes, these are both aligned. They're purely dipolar, even though this is not the dipole that we imagine. So this is closed, only closed lines inside the star. And I don't know if Bruno wants to add something, but in the past we had a paper, Kawamura et al. In 2016, where we also tried different orientation, meaning aligned, misaligned, and both misaligned, and both anti-aligned, say, with respect to the orbital axis. And this had some effect, but not a major effect at the qualitative level. I don't know if Bruno wants to say more.
Okay, thank
Now
you.
let's go on with the question. Maybe this is something I can also discuss further in the discussion session later.
Yeah,
So
point
let's go on with the question. We have a question from Mark.
Yeah, this is a very interesting work. So my question has to do with the growth of the magnetic field through the MRI. It's possible that everything interesting is really happening basically in the first refinement level. But since the overall growth of the structure of the field is both a local and a global, or has local and global behavior, I guess I was wondering if refinement levels introduce a bias in the production of magnetic field energy.
Thank you for your question. As far as I know, I haven't, at least I haven't checked how the MRI is resolved on much higher or bigger refinement levels, so at much larger scale, but I think it should be well resolved. But yeah, this is something that still probably needs to be investigated further. I don't know if, yeah.
Yeah, so
looking back at this, oh, sorry, go ahead.
Yeah, just to specify, yes, so we have quite a few refinement levels up to which this is still well resolved, because we only have factor 2 larger grid cells in next levels, while here we resolve it outside the 10 kilometer, the inner 10 kilometers, with 1,000 to 1,000 points. So this goes up to quite large distance. And of course, where most of the angular momentum resides, all the rotational motion resides, all the rotational energy resides, there we are resolving, as I said, except the inner 10 kilometers.
Okay, thank you.
Okay, next one is Carlos.
Hi. Well, first, thank you for the nice presentation. I would like to ask, in this simulation, did you only try with one resolution? Because it would be very interesting to compare at least with a different resolution, either larger or smaller, but just to see if the time scales and the magnetic field configurations and the effects are still the same, are still showing more or less at the same time, or they are quite different.
Thank you for your question. So I think a couple of runs were also made with different resolutions. So for the resolutions, for the runs, the simulations I talked about during the talk, they had about, in the finest grid was about 220 and 250 meters. But I think Dr. Cholfi also performed simulations with the finer grid, like I think 150 or 175 meters, or so I'm not sure if he probably wants to add more, but I think studies were done. And
yeah, so we have also higher resolutions. The problem is computational resources in this case. We were very limited, so this is not so high resolution, and we just made with a single resolution for the very long time. We also had just up to the early phase of the merger, higher resolution. Of course, we don't see all the interesting effects that Jay discussed. So saturation magnetic field, emergence of magnetically driven outflow, and helical structure at later time. So for that, I don't have a comparison. For the structure of the remnant in the early phase, the qualitative behavior is the same, but of course there are quantitative differences.
thank you.
Okay, thanks.
Okay, and the last question is from Bernard.
Hi, yes, thanks. So I may have missed it, but when looking at the helical structure, the pictures, just when you're talking about helical structure, it seems to be kind of a visual judgment. But is there a quantitative, is there a quantification or some kind of formula that people use when trying to quantify how helical the field has become?
So thank you for your question. So for this plot, as you might see, how we pick or draw these helical structures is, this is something that has been implemented by Wolfgang, and there is this paper, I think, in also discussed in Kawamura 2016. Is what we do is we pick the strongest. We have some seeds, and we pick some of the strongest seeds. The seeds with the having the strongest magnetization, around a particular cone along the spin axis. So this probably gives us these helical structures, but I don't know if there is a quantitative study that has been made, at least not with these simulations, but probably if any other groups has done it, or I'm not sure about that.
Can I
Okay.
So just to quickly say, Bernard, if you're interested in more details, you can have a look at Kamura et al. 2016, because there we also did a more quantitative study. We had a look at essentially how much energy, how much magnetic field was in the different components and also different angles, because we wanted to do something more quantitative than just looking, let's say, at the pictures. So there
okay,
you can find some information.
I'll take a look. Thanks.
Okay, so thanks, Jay, very much. I think we can move to the next talk, which is by Milton.